Okay, guys, we're back at it. 5.1, interesting section. They were having us look at these cubes, and if we dip them in paint, how many faces on each of these little cubes would be painted is what we looked at. So basically, what we discovered was that as long as there's more than two faces, okay, if we have an n by n by n cube, then there will always be 8 cubes with 3 painted faces. Because I'll briefly try to remind you of why. Because for every single cube, the ones that would have 3 faces painted would be the 8 corner pieces. So 4 on the top and 4 on the bottom. So always 8. No matter how big the cube is, there would be 8 of those. Okay? How many had 2 painted faces? That was our B of n. And that one was 12n minus 24. So that's one where that one was a little bit more complicated, I guess. But basically, we would look at how many have just 2 faces painted. So that was these ones. Not these corner ones with the 3 that we previously looked at. So not that, or 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 the one that we can't see in the back. The ones with 2 are, are these. See? 2, 2, and then 2, 2, 2, 2, 2, 2. It's those guys. So we got to take the 2 away from our n. N is the number of cubes that go across. So in this case, it's 4. There would be 2 of them. Okay? So that's how I came to do this. It was the n minus 2. And then on the first face, we've got 4 of those. So it's the n minus 2 times 4. And then on this face, we will have already counted 2 of them. So we have the n minus 2, but this time times only 3 of them. And then that same exact thing will happen one more time on this face, where we're just going to have these 2 already accounted for, and then 1, 2, 3 more sets. So what we just had happens twice. So I multiply by 2. If you prefer, you could just add another 3 times n minus 2. And then by the time we've covered these 3 faces and we get to this face in the back that we can't see, we've already done 2 of them on this side and on this side. So we just have the 2 from the top and the 2 from the bottom. So it's 2 times n minus 2. And that's it. Because once we go all the way around, we've already taken care of the top and the bottom face. So multiplying all this out and simplifying it, I got 12n minus 24. Okay? And then for how many have one face painted, we got ourselves the function c of n being 6 times n minus 2 squared. This one luckily was not as tricky as the last one. So for this one, how many have 2? Well, let's take a look. I'll make it red. It's in the middle, right? It's if we knock one whole dimension off this way, one whole dimension off this way. Okay, so that's the end that we have, but we're subtracting 2 because we're knocking 2 of them out in each direction. And then we have this many, but 6 times. See, every face has one. A cube has 6 faces. So, oh yeah, wait, I'm so sorry. Let's go back. I skipped a step. N minus 2 is one dimension in one direction, but we got to multiply it by the other way, all right, to make a square. This is like a square. So it's the n minus 2 squared times 6. Oh, I already wrote that. And then lastly, how many have 0 painted? Well, if you can remember from the visuals provided in the lesson, it would be much easier. But essentially, if we now look at this and consider like this whole front face, toss it out. This whole face, toss it out. This whole top face, toss it out, toss it out, toss it out, toss it out. Right on the inside of this, we would have a smaller cube whose dimensions are n minus 2 by n minus 2 by n minus 2. In this case, since n is 4, 4 minus 2 is 2, we would have a 2 by 2 cube inside here once we remove all these faces. So it's n minus 2 cubed. And these were the functions that we learned, or derived, I should say. What am I doing? What am I doing? In the previous section, okay? Which are going to help us with the beginning of this assignment. Holy moly. Okay, that was basically a recap of today's lesson in class. Let's do it. Here is a 4 by 4 by 4 painted cube. How many blocks have 6 painted faces? So it's not going to happen. I would say 0. How could every face be painted? The only way that happened, again, if you remember from the lesson, is if we just had a single cube and we dipped it. But as long as they're like this, there's not going to be any cube that doesn't have some portion of it covered. How many blocks have 0 painted faces? Okay, that one we can do. That's this one that we just found, n minus 2 cubed. So n minus 2 cubed. In this case, where n equals 4, because it's a 4 by 4 by 4, this is 4 minus 2 cubed, which is 4 minus 2 is 2 cubed, which is 8, because 2 cubed is 2 times 2 times 2. Okay, here is a 5 by 5 by 5 painted cube. So now our n is 5. And we're going to match the description with the expression that represents it. Fine. What I'm kind of thinking, you guys, is... No, let's just do it. I mean, we can match these up fairly nicely with these formulas. You can also look at the fact that this one is degree 0. This one is degree 1. That one is degree 2. And that one is degree 3. Remember degrees from polynomials? So then here, if you look at this, n is 5. So these 5s are n minus 2, n minus 2. This one is just 8. and there's no n. So this one is linear, degree 1. This one is degree 0. That one is degree 2. And then you could match it up that way, way easier, in my opinion. Otherwise, you just match the format. Okay, it looks like they did rewrite this one. Taking the 12 out, we get 12 times n minus 2. Okay. All right. So 12 times n minus 2 is 2 painted faces. This is B. 8 was the 3 painted faces. That's C. And that leaves this one with the 1 painted face, A. That's it. Matches our formulas. All good to go. Now let's continue looking at a different pattern. Here we've got rectangles. Write an expression for the perimeter of the 1 by 4. So we've got the 1 times 2, because there's 2 of them. And then we've got the 4 times 2. So let's just say 2 times 1 plus 2 times 4. You may also write it as 2 times 1 plus 4 by taking the 2 out. Whatever way makes sense to you, it's fine. But using those expressions, we can do it for a 1 by 10 without drawing it and looking at it that way. So we could do 2 times 1 plus 2 times 10, or you might just go straight to 2 times 11, or 1 plus 10. So now let's write a function to determine the perimeter of a 1 by n rectangle. So that would be 2 times 1 plus 2 times n. And we could write this nicer, 2 plus 2n. That works. Or if you did this one, it would be 2 times n plus 1. All of those are okay. The 1 by 4 rectangle has 3 line segments that are not on the perimeter. Write a function to determine the number of line segments in a 1 by n rectangle that's not on the perimeter. Okay, let's go look at what they're talking about. And this is what they're talking about. They're talking about how here there's 1, 2, 3 little lines in the middle that aren't part of it. When it was a 1 by 3, there was 2 of them. When it was a 1 by 2, there was only 1. And when it was a 1 by 1, there wasn't any. So it's looking to me like it's always 1 less than that number. You see, just 1 less than that number. So you're just looking for a pattern, you guys. So if it's a 1 by n, then we're looking at what's 1 less than n. Remember those expressions from like middle school that they would want you to write? What is 1 less than n? That's n minus 1. So there's n minus 1 of those. Okie doke. Back to the cubes. Here's a pattern of painted rectangular. Oh no, they're not cubes. They're rectangular prisms. I didn't catch that. The length is always 3. So this one is a 3 by 1 by 1. This is a 3 by 2 by 2, 3 by 3 by 3, 3 by 4 by 4, and so on. So 3 by n by n. How many blocks with 1 painted face are there in a 3 by 4 by 4? Okay, let's go do this. So we do have the ones, okay, this is different. This is totally different. But should we just look at this one? The one they said, let's see if we can figure it out just from that. How many have 1 painted face? So it's not going to be these corner pieces that have 3. Okay. And it's not going to be any of these edge pieces at all, actually. Okay, it's just going to be what's in the center. When we take one away, no, do we take one away from every side? We take two away from every side. Okay, so if I subtract 2 from every side, I get a 1 by 2. On this side, though, only. Oh, yeah, and then over here, it's 2 by 2. Okay, so that can't be trusted. So let's look. So right here, it's a 1 by 2. So there's 2 of them on this face. Same will be true for the face behind it. So it's 2 times 2. Same is true for here, 3, and on the bottom 4. So 2 times 4. That's 8 of them. Like here, 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 and here. And then on this face, because this isn't uniform, we have the 4 faces that are the same like that, and then we've got 2 faces that are the same like this. On these guys, we've got 2 by 2. So that's 4, and I have 2 of those. So that's another 8, and that makes 16. Okay. How many blocks with one painted face are in a 3 by 5 by 5? So I'm just trying to see here, the 3 by 4 was this 3 by 4, and we had 4 of those. So here, the 3 by 5, we're going to have 4 of those. And then the 5 by 5, we're going to have 2 of those. Okay? So on the 3 by 5, let's see if I can manage to draw this. 1, 2, 3, 4. On that one, we're gonna not be those. We're gonna have this right here going on. So subtract 2. Subtract 2. We have 1 by 3. See? 4 of those. So that's 12. And then the 5 by 5 faces, you may not need this drawing anymore, but I'm still gonna draw it. Once you take this out and this out and this out and this out, you've got yourself a 3 by 3. See? Subtract 2, subtract 2. That makes a 3 by 3, but we only have 2 of those. So that's 9 times 2, 18. So altogether, that's 12 and 18, which is 30 of them. So now that we've done this a couple of times, let's write a function to determine the number of blocks with one painted face. Here we go. I'm going to take this 3 by n, and I'm going to subtract 2. Subtract 2, subtract 2 to make it a 1 by n minus 2. And then we're going to have how many of those faces, if you remember? That's this part, 4 of them. And then we're also going to have 2 faces that are n minus 2 by n minus 2. So n minus 2 squared. Okay. Trying to think what's the better way. Let's keep going with this. So this right here, simplify it down. This is 4 times n minus 2 plus, and this one is 2 times n minus 2 squared. And we could leave it like this. I'm going to leave it like this. I don't see the problem. So 4 times n minus 2 plus 2 times n minus 2 squared. And now we've got some spiral review going. Here are two functions, x plus 2 and x minus 2. Complete the table, graph both functions. Oh, this is it's good. I like it. Let's look at these two real quick. If I plug in a -1 here, -1 plus 2 is 1. 0 plus 2 is 2, and 1 plus 2 is 3. So there's the table. And I can graph this, -1, 1, 0, 2. Man, this graph is tiny. And 1, 3. And then we could draw ourselves a really pretty line. Through them, right? Come on, focus. There we go. Woo. Okay, shaky start, but we got it. And now let's go do this one. -1 plugged in here, that's -3. 0 minus 2, -2. 1 minus 2, -1. Let's plot that guy. So that's -1, -1, 2, 3. This is 0, -2. And this is 1, -1. Oh, man. Okay. And these guys are... I don't know that this was the best example. But it's not a bad example. I will bring up something. Why did the spiral review throw this in out of nowhere? There's usually a method to their madness. You may not remember, or you may not remember, f of x equals x plus 2 and g of x equals x minus 2. These functions are actually inverses of one another. And we're going to dig into what that means and how we find them and all that kind of good stuff. But these are inverses. And then what happens with an inverse is that, and the table that they gave doesn't even show it, but basically their x's and y's are switched. Okay? So, like, for example, if this guy has a point on it that's 1, 3, then this guy has a point on it that's 3, 1. Just switch the x and y, and look, 1, 2, 3, 1 is a point on that graph. And every point would have that property going for it, okay? So that's what inverses are. X's and y switch. And then this red line that I graphed is the line y equals x. So because the x and y switches, two functions, if they are inverses of each other, they are just reflection over the line y equals x. So you could tell if we reflected this blue line over the red line, we would get the green line. So just a quick little bit of inverse talk to think about, to just see, and then once we go into it more and more, it'll make more sense. But hopefully seeing it for a little bit right now helps for when that happens. Okay, guys.